Neutron stars are among the most mysterious objects in the vast universe. They are celestial bodies of extreme density and gravity. These enigmatic objects are born from the death throes of massive stars. Their existence pushes the boundaries of physics as we know it. Imagine a star more massive than our sun, squeezed into a sphere the size of a city. That's a neutron star. In the cosmic tapestry of stars, galaxies, and black holes, neutron stars hold a special place. They are remnants of stellar explosions, marking the end of a star's life cycle. These stellar corpses are not just fascinating for their extreme properties, they also serve as cosmic laboratories. Neutron stars provide us with insights into the fundamental laws of nature. As we delve deeper into the realm of neutron stars, prepare to be amazed by their mind-boggling characteristics. Their study offers a glimpse into the most extreme environments in the universe. The journey promises to be an exciting exploration of the cosmos. The story of a neutron star begins with the death of a giant star. When a star much more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against gravity. The core of the star collapses under its own weight. This collapse triggers a catastrophic explosion known as a supernova. During a supernova, the outer layers of the star are blasted into space. Meanwhile, the core continues to collapse. The intense pressure within the collapsing core forces protons and electrons to combine. This forms neutrons, hence the name neutron star. These neutrons, packed together as tightly as the laws of physics allow, resist further collapse. This resistance arises from a quantum mechanical effect known as neutron degeneracy pressure. This pressure prevents the neutron star from collapsing into a black hole. However, this only holds true if the core's mass is below a certain limit. Neutron stars are incredibly dense. Imagine squeezing the mass of our Sun, which is about 333,000 times the mass of Earth, into a sphere with a radius of only about 10 kilometers. That's the density of a neutron star. A teaspoonful of neutron star material would weigh billions of tons on Earth. The intense gravity of a neutron star warps space-time around it. This warping is so strong that it can bend light. Imagine standing on the surface of a neutron star. If you could, you would experience a gravitational pull billions of times stronger than Earth's gravity. Neutron stars are also incredibly hot. Their surface temperature can reach millions of degrees Celsius. This heat is generated by the decay of radioactive elements formed during the supernova explosion. Despite their small size, neutron stars are incredibly bright. They emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. The journey to becoming a neutron star begins with a spectacular demise. Massive stars, those at least 8 times the mass of our Sun, live fast and die young. They burn through their nuclear fuel much faster than their smaller counterparts. As the star's core runs out of fuel, the outward pressure from nuclear fusion can no longer counteract the immense inward pull of gravity. This imbalance triggers a chain reaction that leads to a catastrophic event, a supernova explosion. The core collapses in on itself, reaching incredibly high temperatures and densities. This collapse happens in a fraction of a second, generating a shock wave that travels through the star at nearly the speed of light. The shock wave tears through the outer layers of the star, blasting them out into space in a brilliant display of cosmic fireworks. This explosion is so powerful that it can outshine an entire galaxy for a brief period. It is during this violent death that the seeds of a neutron star are sown. At the heart of the exploding star, a dramatic transformation is taking place. The immense pressure from the collapsing core forces atoms together, overcoming the electromagnetic force that normally keeps them apart. Electrons are forced into the atomic nuclei, where they combine with protons to form neutrons. This process, known as neutronization, releases a tremendous amount of energy in the form of neutrinos. Neutrinos are tiny, nearly massless particles that interact very weakly with matter. They escape from the collapsing core, carrying away a significant fraction of the star's energy. As more and more neutrons are formed, they are squeezed together into an incredibly dense state. The density at the core becomes so extreme that a teaspoonful of this neutron-rich material would weigh billions of tons on Earth. It is within this dense, hot cauldron that a neutron star is about to be born. The relentless crush of gravity continues to push inward, threatening to collapse the core into oblivion. However, a new force emerges to oppose gravity's pull: neutron degeneracy pressure. This pressure arises from the quantum mechanical behavior of neutrons. According to the Pauli exclusion principle, no two neutrons can occupy the same quantum state. In other words, neutrons, like tiny hard spheres, resist being squeezed too close together. This resistance to compression creates an outward pressure that can counteract the inward pull of gravity. However, this balancing act has its limits. If the mass of the collapsing core exceeds a critical threshold, known as the Tolman-Oppenheimer-Volkoff limit, neutron degeneracy pressure is not enough to prevent further collapse. In such cases, the core continues to collapse, eventually forming a black hole. If the collapsing core's mass is below the critical limit, neutron degeneracy pressure halts the collapse, leaving behind an incredibly dense, compact object, a neutron star. The newly born neutron star is extremely hot, with temperatures reaching millions of degrees Celsius. It spins rapidly, a consequence of the conservation of angular momentum as the core collapsed. Over time, the neutron star cools down, radiating away its thermal energy. It also gradually slows down its rotation due to interactions with its surroundings. However, even as it cools and slows down, the neutron star remains an incredibly extreme object with properties unlike anything found on Earth. The birth of a neutron star marks the end of one star's life and the beginning of a new chapter in the cosmic story. These dense remnants of stellar explosions continue to fascinate and challenge our understanding of the universe, offering insights into the fundamental laws of physics under the most extreme conditions. Cosmic compactness, size and density. Neutron stars are incredibly massive, yet incredibly small. Imagine squeezing all the mass of our Sun into a sphere about 20 kilometers in diameter. A single teaspoonful of neutron star material would weigh billions of tons on Earth. Gravitational giants, surface gravity. Neutron stars have incredibly strong gravity. Their surface gravity is about 200 billion times stronger than Earth's. An object dropped from 1 meter would hit the surface in less than a millionth of a second. This gravity warps space-time significantly. It can even bend light, acting like a gravitational lens. At extreme temperatures and luminosity. The birth of a neutron star in a supernova explosion is a tremendously energetic event, heating the newly formed neutron star to incredibly high temperatures. Initially, the surface temperature of a neutron star can reach billions of degrees Celsius, hotter than the core of our Sun. As neutron stars age, they gradually cool down, radiating away their thermal energy into space. However, even after millions of years, neutron stars remain incredibly hot, with surface temperatures of millions of degrees Celsius. This intense heat causes neutron stars to glow brightly in X-rays and other high-energy forms of radiation. Despite their high temperatures, neutron stars are incredibly faint objects, difficult to detect even with powerful telescopes. This is because their small size means they have a very small surface area from which to radiate energy. However, the intense radiation they emit provides valuable clues about their extreme properties and the physical processes occurring within them. Section 4. The composition and structure of neutron stars. The interior of a neutron star is hidden by extreme density and gravity. Scientists have developed models based on nuclear physics and extreme conditions. The outermost layer is a thin crust of heavy atomic nuclei, primarily iron. Beneath lies a sea of superfluid neutrons, flowing without resistance. Deeper density and pressure become so extreme that physics breaks down. The core may contain exotic matter like hyperons or deconfined quark matter. Studying neutron stars pushes the boundaries of our understanding of fundamental physics. Section 1. Pulsars, cosmic lighthouses. Pulsars are fascinating neutron stars. They spin rapidly, emitting beams of radiation. Imagine a lighthouse beacon sweeping across the ocean. Similarly, pulsar beams sweep across space. If Earth lies in their path, we detect pulses of radiation. Jocelyn Bell Burnell discovered pulsars in 1967. Initially, some thought they were extraterrestrial signals, but they are natural phenomena from rotating neutron stars. Magnetars, magnetic powerhouses. Magnetars are cosmic magnets on steroids. They possess the strongest magnetic fields ever observed, up to a quadrillion times stronger than Earth's. Imagine a magnet so powerful it distorts atoms from thousands of kilometers away. That's the power of a magnetar. The origin of these fields is still a mystery, linked to neutron star formation. They generate high-energy radiation, including gamma rays and X-rays. Magnetars can release giant flares, emitting immense energy in seconds. Not all neutron stars live solitary lives. Some exist in binary systems locked in a gravitational dance with a companion star. In these systems, known as X-ray binaries, the neutron star's intense gravity can pull material from its companion star, forming an accretion disk of hot gas spiraling around the neutron star. As the material in the accretion disk falls towards the neutron star, it heats up to millions of degrees Celsius, emitting X-rays. These X-ray emissions are so powerful that X-ray binaries are among the brightest objects in the X-ray sky. X-ray binaries provide a unique laboratory for studying the physics of accretion, the process by which objects grow by accumulating matter from their surroundings. They also offer insights into the behavior of matter under extreme gravity and magnetic fields. By observing the X-ray emissions from these systems, astronomers can learn about the properties of the neutron star, such as its mass and spin rate. As pulsars age, they gradually slow down their rotation as they lose energy through radiation. However, some pulsars, known as millisecond pulsars, spin incredibly fast with rotation periods of just a few milliseconds. These pulsars are thought to be spun up by accreting material from a companion star in a binary system. As material falls onto the neutron star, it transfers angular momentum, causing the neutron star to spin faster and faster. This process can spin up a pulsar to millisecond periods over millions of years. Millisecond pulsars are incredibly precise timekeepers, with some of them rivaling the accuracy of atomic clocks. This precision makes them valuable tools for studying a wide range of astrophysical phenomena, including tests of general relativity, the detection of gravitational waves, and the mapping of the interstellar medium. The study of different types of neutron stars, from pulsars to magnetars to X-ray binaries, provides a window into the most extreme environments in the universe. Neutron stars possess magnetic fields of astonishing strength, a direct consequence of the star's collapse. Magnetars, a type of neutron star, have magnetic fields reaching up to a quadrillion Gauss, causing starquakes and releasing enormous bursts of energy. The intense magnetic fields of neutron stars accelerate charged particles, emitting radiation across the electromagnetic spectrum. Pulsars, rapidly rotating neutron stars, emit beams of radiation, providing valuable information about their properties and the surrounding environment. Neutron stars are some of the fastest spinning objects in the universe, a result of the conservation of angular momentum during the star's collapse. The fastest spinning neutron star, PSR J 1748-2446 AD, rotates at 716 times per second, affecting its properties and behavior. Millisecond pulsars spin hundreds of times per second, pushing the limits of rotation. These pulsars are spun up over millions of years by accreting material from a companion star. Their precision makes them valuable tools for astrophysical studies, including tests of general relativity and the search for gravitational waves. Exploring a neutron star is like diving into the ocean, descending through layers of increasing pressure and darkness. The structure of a neutron star is layered, with each layer characterized by distinct properties and composition. The core of a neutron star is a place of extremes where matter is compressed to densities far beyond anything achievable on Earth. Scientists rely on theoretical models, computer simulations, and observations to probe the mysteries of the core. The composition of a neutron star is as intriguing as its structure, with neutrons dominating the interior. Theories suggest the core could be composed of free quarks or even more exotic particles, adding complexity to the neutron star's composition. The study of neutron star composition and structure is a journey into uncharted territory. Astronomers and physicists use observations and theoretical models to predict the properties of matter under extreme density and pressure. Despite their size and distance, neutron stars are not entirely hidden from our view. Astronomers use a wide range of telescopes and instruments to study neutron stars across the electromagnetic spectrum. Neutron stars provide unique environments to test the laws of physics under extreme conditions. Observations of binary pulsars allow astronomers to measure the effects of gravity on spacetime, confirming general relativity. Neutron stars play an active role in shaping the universe, influencing the evolution of galaxies and the formation of heavy elements. Their energetic emissions can heat and ionize interstellar gas, affecting star formation and galaxy evolution. The study of neutron stars is an ongoing journey, with new telescopes and instruments promising to revolutionize our view. Gravitational wave astronomy and advances in theoretical modeling are enhancing our understanding of these extreme objects. Neutron stars stand out as beacons of extreme physics, pushing the boundaries of our understanding of the universe. Their extreme properties make them fascinating objects of study and cosmic laboratories for testing the limits of physics. For Section 2, Unraveling the Cosmos, the importance of neutron star research. Neutron stars provide insights into the life cycles of stars, the formation of heavy elements, and the dynamics of galaxies. Observing neutron stars reveals processes during massive star deaths, and neutron star mergers shed light on heavy elements like gold and platinum. They serve as cosmic labs for testing fundamental physics. Section 3, Lingering Mysteries and Future Explorations. Neutron stars hold many mysteries, urging us to delve deeper into their enigmatic realms. Their core composition and structure challenge our understanding of matter. Gravitational wave astronomy offers unprecedented insights into neutron star mergers. New data will revolutionize our understanding of these enigmatic objects. Future telescopes promise to reveal neutron stars in greater detail.
Like and subscribe to start your journey today.